Hello everyone. Welcome to the EasyPower Thursday Technical Webinar Series. My name is Jim Chastain. I'm your host for today's session. We appreciate your attendance. And before I hand the podium over to our guest speaker on fuse construction, performance, and applications, I'd like to run a couple poll questions to get a little bit of a perspective on where the audience stands on the topic. So if you would please help us by responding in kind. And the first question is, what does UL do? Which I'm sure is something that puzzles a lot of us. So again, there's no obligation, no liability. It's strictly just taking a swipe at what kind of information you're aware of. Just for housekeeping purposes, all attendees today will receive an attendance certificate that many use to support their ECU credits. Those will be sent to you automatically. You don't have to do a thing about it. Okay, looks like we have a quorum here. Let's see how people have weighed in. So it looks like there's a fairly strong majority with the opinion that Underwriters does something. That's good. The next question is, how often does the National Electrical Code change? This may be a little bit more taxing for some of us. And we do appreciate your attending these webinars. And certainly if you have suggestions for other topics or other areas that you'd like to see presentations on, feel free to drop us a line, jim@easypower.com, and we will try to accommodate you. Okay, so it looks like we have a quorum here. Here's how folks have weighed in. Looks like we have a strong majority there for 3 years. That's excellent. And then finally, what quenches an arc? And we get some interesting choices. So I'm sure it's testing some of us. Looks like we're close to 50%. Let's give this another 8 seconds. Here are the results here. So this is a little bit more challenging. So we look forward to the presentation to clear this up. So our speaker today is a solutions engineer with Mersen USA. And at this time, I'd like to turn the presentation over to him. Brad, you have the baton.
Can you see my screen?
Yep, looks beautiful.
Okay. Shout out to whoever chose magic. That was for quenching an arc. That was a solid answer. So today we're going to go over just the fuse basics. So we're going to start with construction, performance, and then we're going to get a little more taxing and go into the actual applications themselves and use a few code articles to show why we come up with the sizing that we actually do. At the end of the day, I don't expect you guys to be doing this kind of stuff by yourself. We're always available at Mersen to help you guys with any kind of application needs that you guys have. So with that, first things first, let's start off with as basic as I could get and how to read a label. So this is going to be an A4BQ. You can see the name of the fuse right there. It's going to be a 1200 amp fuse. Just underneath that is going to be a reference number. That's going to be for us so that we know what fuses have been tested to what specifications and to make sure that they actually meet those. And under that, you're going to have the ampacity. So this is going to be a 1200 amp fuse. On the left side of this is going to be the front of the fuse. So you can see that this is going to be an amp trap 2000. Just below the indicator, you're going to see it's going to be a 600 amps or 600 volts or less time delayed fuse. And then on the right, this will be the back of the fuse. So you'll see that this is a class L fuse. It's going to have a 200,000 amp interrupting rating at 600 volts AC and 1,000 amps interrupting rating at 500 volts DC. What that essentially means is what this fuse can safely open before it just becomes a bomb. So at Mersen, UL says that we're required to do, or the UL says that we're required to do 200,000 amps interrupting rating. We do self-certify at 300,000 amps. We like to go above and beyond and just make sure that that our fuse is safe for all applications. You are going to see that this is a current limiting fuse, and then under that you're going to have the certifications for this. You can go to the UL website and type in this issue number, and it'll bring up the different various testing that we actually do on this to make sure that it is certified. And then on the side of the fuse is where we are going to be located in Newburyport, Massachusetts, as well as our website. One of the features that we put in to be NFPA 70E compliant is rejection features. So you can see here that we have 3 different styles of fuses with 3 different rejection styles. All of these are going to be 30 amp fuses. On the bottom, you can see this rejection style ferrule. On the AJT30, we're going to have a rejection by size feature. And then on the right here, you can see the ATDR30 has a rejection style feature on that as well. One of the engineering mitigation factors that we also use is rejection by size. So as an ampacity goes up, and this kind of makes sense after we go through the construction, as the ampacity goes up, the fuse body gets bigger. So when the body gets bigger, it goes into a different holder. So it allows, or it'll restrict the end users from putting the wrong ampacity into the wrong holder. But you know, there's still misapplications out there. It can still be done through you know, street engineering, but this is just something that we do for our end users so that they'll be more protected in the field. So let's get into the actual construction of these fuses themselves. So on one side, we're going to have our block. We're going to braze on our blade, and then inside we're going to have the element itself. This is where the magic happens. So if we want to have a 400 amp fuse and this is a 100 amp element, we're just going to put 4 of these elements in parallel. We'll have another blaze block assembly on the other side, and then we'll put our body on it. Inside the body is where we're going to have a filler, and this is going to be the sand that we actually make ourselves, take out all the impurities. It's not going to be like beach sand or anything like that. And the reason for that, whenever the arc comes in contact with the sand that's inside, it'll turn into a glass or into an insulating material, and it'll open the circuit. So in the case of a short circuit, which we'll kind of get into in a little bit, it'll cover the entire element. With the time delay, it's going to be a little bit different. So we have a piece of eudectic solder here in the middle, and with that, the principle applies that whenever current is flowing across this, it's not going to be the 10 times rated of the fuse to actually open up and burn away this material. It's just going to be enough to put energy into this piece of solder, right? So any guys that have ever soldered, you take the iron, you put it to the solder. As the heat increases, you'll change the state from a solid to a liquid. Once it turns into a liquid, it'll go away. The arc will continue to flow over the gap. It'll come in contact with that filler or the sand and insulate the circuit. Getting into our RK1 styles, you're going to have our spring plunger assembly, and inside you're going to have a spring. Now the key is going to be that this is a compressed spring, and that'll make sense in a second. Then we're going to have our plunger, our heater connected to the outside, and then our short circuit element. So the same thing kind of applies with this, where we have our piece of solder here. So in the case of an overload where you're not at the 10 times rated, but you're outside the band of normal operation, you're going to have this piece of solder start to heat up. The solder will turn into a liquid. Once it does, this compressed spring will pull the plunger forward, opening the circuit. We have a grommet to make sure that everything stays in place. And then we have our body that goes on the outside, fiberglass washer on our end, a rejection style ferrule, and then the filler that goes inside, which is going to be that purified sand, our fiberglass washer for the other end, and then our non-rejection style ferrule. So getting into medium voltage fuses, this is going to be what the interior looks like. We're going to have our stabilizers that keep everything in place, the ends that will actually connect into the application itself, and then our elements. So say that this element is going to be a 100 amp element and you want a 400 amp fuse. We're just going to have 4 of these in parallel as they wrap around. So the same principle applies. These are going to be the short circuit elements in here. So in the case of a fault, these will be wrapped in that sandy material. But we're going to have our end on one side and then our body that goes around it, and then our encapsulated. So now kind of getting into our time current curves, I'm not going to expect you guys to remember this, but I do expect you guys to kind of know that this is available. If you go onto our website and you type in the AJT 100, it's going to bring up the data sheet on this, and then underneath it, it's going to bring up the time current curve and the peak let through curves, and we're going to go through those right now. But just remember that you have to put in the exact part number that you're looking for. You know, if it's the AJT 25 or the AJT 100, if you just type in the AJT, you're not going to see any time current curves. So this is how they work. On the bottom is going to be the RMS value, and on the left is going to be the time in which it'll actually open. So this is going to be 100, 200, 300, 400. You go up to where it crosses over the curve, and this is going to open in 10, 20, 30 seconds. So whenever you're trying to selectively coordinate an application, this is the kind of information that you're going to be looking for. Getting into the peak let-through current, and this is how much current an end device will possibly see. So we're going to have our your curve, which is the AJT 100. You're going to come up from the bottom, which is going to be your RMS value, and on the left is going to be your peak. So you have 10, 20, 30, 40, 50,000 amps, come up to where it crosses the line, and it's going to be about 9,000 amps. But if you want to know what that is in RMS value, we put in this gray line, and where it comes back down is going to be the amount in RMS, so you don't have to do any kind of calculations or anything, even though sometimes that's fun. It'll be about 4,000 amps RMS. Looking at theoretical, we're going to get into how a fuse actually clears. So on the left is going to be the full load amps. On the dotted line is going to be the available fault current. And right here, this little parabola that's in blue in the first quarter wave cycle of this, the available fault current is going to be the let through. And let's kind of take a closer look at that. So this is going to be known as the peak let through current. And this is going to be during normal operation. This is the short circuit current element. You can see that all the holes are open. There's no issues. The overload element is going to be on the side. You can notice that there's going to be a small volume of metal here. What happens is that's going to vaporize once it reaches too high of a current. So let's take a look at a fault. The first half of this is going to be known as the melting I squared T. It's how much energy is going to be flowing through the element. It's going to jump across all these holes, vaporizing all that material, and essentially coming in contact with that filler. Once it does, the second half of this is going to be the clearing I squared T, which is how much time it takes to vaporize that material, come in contact with the filler, and turn into an insulating material. So now you can see this is what that sand will actually look like, or the magic that happens inside of this fuse. So getting into the applications, we're going to go over two types of applications, and I'm going to stay kind of broad on these, but if you guys have any questions on this, I'll point you in the right direction as far as literature goes. So we're going to go with motor starting characteristics, the difference between type 1 and type 2 protection, and then we're going to jump into transformers. So first, taking a look at a motor. So this is from a motor when it has the lock rotor current, where it's actually stopped and how much energy it takes to start it. So once it starts, that current is the inrush is going to peak pretty high for about 2 to 10 seconds before it comes into normal operation or the full load amps. And what we want is a fuse that is not going to necessarily open during the lock current part of this. It's going to wait until the full load, and then if there is going to be any kind of an issue, then you want your fuse to open. The different types of fuses that we offer for motors is going to be our LSJs, CCs, RK5s, and RK1s. So taking a look, we're just going to throw out some numbers right now. So we're going to have a 480 amp, or sorry, a 480 volt circuit, 50 horsepower. So your full load amps on this is going to be 65. So according to Article 430.32 of the NEC, fuses can be provided the overload protection and the short circuit current protection, but they must be sized at 125% of the FLA. So with that, we'll take our 65, multiply it by 125, or sorry, yeah, by 125, I'll give us 81.25, and we're allowed to go up to the next size up, so that's going to be our AJT 90. Sticking with the same numbers here, you're allowed to have 125% if it's going to be provided the overload protection, and the short circuit current protection. But if you're going to be using a time delayed fuse, you want to do 175%. If it's going to be non-time delayed, it's going to be 300%. So let's take a look at some of those numbers. Also, this is all going to be in our advisor, and it's also available online. So if you guys have any questions on this, you're not going to have to do any of the math yourself, and we're always available to help you as well. Taking a look at the time current curves for this, so we're going to have the AJT100 and the A4J100 with a NEMA 20 class overload relay. So with the overload relay, say you have your start coming in, and you can see right here at the A4J, these are all going to be sized at 150%, which is inside the maximum of 300%. You can see that the A4J is going to clearly open upon start, and we can't have that because this is going to be normal operation. There's not going to be any kind of an issue. So according to 430.32, we're allowed to go up to 300%. So if we move that to the 300%, it'll take that A4J and move it to a A4J200, which will allow us to stay. So you can see that the overload relay will actually open before that or faster. The overload will open faster than the A4J, and that's what we want. We want this thing to go into normal operation before we have any kind of a fault. So now getting into some actual videos on this, I'm just going to go ahead and let these play. This is going to be your type 1 protection versus type 2 protection. So as you can see, notice that there's going to be a flash on the fuses themselves in this application. Right now what we're looking at is the type 2 protection, which will allow both of these to operate correctly. So type 1 protection means that this has to open at all costs, and there's going to be damage to some of the equipment. This is a proper UL application. So this is with a breaker in place and an overload relay down below. And that is considered a UL application that is proper. So with fuses, this will actually, the fuses will protect to make sure that overload relay does not explode. So now type 2 coordination protection with fuses and an IEC contactor with an overload relay. Notice again that there's going to be a flash on the indicators for the fusing in this application. See, now that it's safely open, no damage to the overload relay, the system worked just fine. So now type 1 coordination protection with a proper circuit breaker and an IEC rated contactor for an overload. This again is also a proper UL application. So you can see the difference. The fuse is actually opened to protect the overload relay, where the breaker did not. Now, I believe some of the newer, smarter breakers out there might be able to handle this, but fuses are going to be the route. They're going to be the way to help you so you're not damaging any equipment that is actually involved in the system. So now the difference between type 1 coordination protection and type 2. As you can see, the overload relay was not damaged. The circuit was opened and there was no fault. So now we're going to go with type 1 coordination protection with a circuit breaker and a NEMA rated contactor with an overload. And again, this is a proper UL application. So down the line, the motor should be fine, but again, you're damaging equipment inside. Now this has to be replaced and fixed up. So again, the manufacturers usually are going to tell you inside of their literature what style of fuse that they believe that you should use or that they want you to use for the application, and you should always go with what they say because they've done testing to verify that. At Mersen, we usually collect the data on this different stuff ourselves. We will offer you the information for whatever the application is. We will help you find what the fuse is and size it correctly so that you're not damaging any equipment and that you do get the information. This is also all available online on our website, but upon request, we can get it to you as well. So medium voltage protection. In this application, you're not allowed to use a fuse for overload. You're supposed to be using R-rated fuses for short circuit current protection only, which means that they're required to have an overload relay to protect any medium voltage application. So let's jump into a transformer. So what is a transformer? It's used to either increase or decrease voltage and current inversely. There's going to be a wide range on these, but for us, we're just going to focus on certain kind of applications. So with that, we're going to go with the 0.01, which is going to be about 25% of the FLA. For 0.01 seconds, you're going to be at about 25%. So when you're sizing these, you want to make sure that your time current curve is to the right of whatever's coming in. And we'll take a look at this in a second. You're going to want, for 0.1 seconds, 12 times the full load amp. So what style of fuses do we actually have for this? We have our L's, J's, CC's, RK5s, and RK1s. So let's get into the fun part with some math. We have a 75 kA three-phase 480 volt transformer. So we're going to try and determine what the actual current output on this is going to be. So you take your transformer VA, multiply it by 1,000, divide it by the square root of 3, multiply it by 480, and you're going to get around 90 amps on the primary. So on the secondary, you're going to get 75 kA multiplied by, or 75 volt amps multiplied by your 1,000. And then you're going to divide that by the square root of 3 multiplied by the secondary voltage. So you get about 208 amps. So if you're only doing the primary fuses, you do 125% for primary only. So you take your 90 amps, multiply it by 125, you're going to get about 112.5 amps. So the fuse we're going to use for this, you go the next size up, is going to be the TRS 125R. And again, we have literature on this. This will all be available to you, and it'll lay it out in a very clean manner. We'll actually tell you the kVA of the fuse or the transformer, and then you just go along the side to what you're actually protecting. So getting into primary and secondary fusing. So this is where you're going to want to do 250% of the full load for primary and secondary. So for the primary, you're going to have your 90 amps at 250%. It's going to be the TRS 225. So the secondary, you can have 125% of the full load. So you have your 208, which will be 260.5 amps. So you go to the next size up, that'll be the TRS 300R. And again, the literature is going to be available online. We're not going to expect you to calculate all this stuff. So what is this actually going to look like on a time current curve? So you have your TRS 125, and then you're going to have your inrush. So you can see that during that 0.1 seconds at the 25 times and the 0.01 seconds, or sorry, 0.01 seconds at 25 and the 12 times at the 0.1 seconds, we're going to be to the right of all of that on the time current curves. So now dealing with the inrush, this is going to be the medium voltage fuses that we actually offer. These fuses are going to be rated for low voltage, and usually for transformers, they're going to want to go with the E-rated style fuses. So what do we offer? It's going to be our 9F series. So if you take a look at these, the voltage is going to be right here. So you have your 825, which will be your 8.25 kVA, and then this is going to be a 30 E-rated fuse. And on this one, you're going to have 7.2 kVA, 2-barrel, and then down the line is going to be your 350E. So this is going to be the 9F series. It's also known as the the EJ01 type. This is going to be for general purpose. They are going to be UL listed. Indoor, outdoor use, 5.5 kVA, 25 amps up to 900, 8.3 kVA for 20 amps up to 250, and for 15.5 kV, we're going to have 20 amps up to 300 amps. Getting into the 9F line, this would be the 9F60 series or the EJ01 type. This is going to be for power distribution fuses. These are going to be our E-rated. These are going to be for indoor, outdoor use, and we have a wide range of different styles for these. So getting into the actual guides for these, this is going to be the tables taken from 450.3 of the NEC, and these are also available in the Mersen Advisor. So you can see that it's going to be specified as far as the primary fuses. Oh, sorry. For primary fuses up to 300%, the secondary fuses up to 250. If it's going to be over 600 volts, for under 600 volts will be 125, and these are for unsupervised locations. For the table 4 is going to be your supervised, and it's going to be for all fuses is going to be 250 or 300%. If it's going to be 6% impedance or less, and then in the secondary for over 600 volts will be 250. And also for 600 amps or less. And where the fuses do not correspond with the standard size, so if you get like a weird number, it is okay to go up to the next highest standard. So in the actual advisor ourselves and online, you're going to see how these are actually laid out. So on the left is going to be the transformer rating in kVA, which this will be your 300, and then our full load amps, and then there'll be the different styles of fuses based on the ferrule types that we're actually going to have for these. If they're going to be bolt-on or clip-in, and the different applications we have. So it kind of explains itself inside of the tables. There's going to be a wide range of tables available, and if you need these, we can get them to you. They're available online, but upon request, we can get you any information that you need for this. So what other resources do you guys have? Our website is dedicated to you guys. We have data sheets, brochures, tech topics, white papers, flyers, fact sheets, line cards, and installation guides as well. Your rep is usually going to be a pretty good help for you guys that can usually point you in the direction of the solutions engineer in your area, or you can contact our tech services directly. I cover the West Coast, but I can help anybody. I can point you in the right direction and get you as much help as you guys need. We also have our product managers that are available if you guys have any kind of information or testing that you need that we do not provide online, or we do not have this kind of off the wall, depending on if the application's strange, we can usually get a hold of them and get whatever that testing is conducted for you. So I know that was kind of fast, but do you guys have any questions or anything that you would like to talk about? Awesome. I appreciate you guys taking the time today. And again, my information is available. I'll put it up right here. It's also in that PDF. If you guys have any questions you want to talk offline or anything like that, let me know. I'm available whenever you guys need me.
Thanks, Brad. That was a lot of information in a short amount of time.
Yeah, sorry. It gets pretty complicated. At the end of the day, I don't expect you guys to remember everything that was there. Just remember that we do provide it, and that we can get you that information. So when you run into the problem, just be like, oh yeah, the Mersen guy, he knows. He'll be able to figure out what this is. And that's usually when we get the questions. You don't have to remember the exact numbers, although it is in the NEC. We will provide all that for you. It's just good to know when you have an issue that you do have support.
There is a question here, Brad, from Robert. He's asking, how do you model parallel fuses?
Usually we don't model. So we have a testing facility out in Newburyport where we will actually physically do the testing themselves. We will put them, we'll come up with a theory where we think is going to happen, base the actual numbers on what we think is going to happen, but then we'll conduct the test itself to verify that information. And we'll go off of what the test actually is instead of just the theory of what we were trying to do.
How do you model current limiting resistors or current limiters?
So again, with modeling, what we usually do is we build the element based on what it's going to be able to tolerate. You know, how many holes it's going to have, the cross-sectional area, and then we actually will physically test it to make sure that it will limit the current down to a safe, manageable level. So based on the amount of holes that it'll have on the short circuit current element, it will allow a certain amount of current to pass through it before it vaporizes the material. So you know what kind of material that you have, the cross-sectional area, the diameter of the holes, the amount of material that's actually in between those holes. And then once we test it, we can determine how much the peak let-through current is going to be. So we'll, on our website, say you're looking at the AJT 100, it'll have the peak let-through current, so it'll show you how much of that value actually will come down and how much the end device will actually see.
So that doesn't affect the TCC curve.
No, the TCC curve and the peak let through current are two different curves.
Right.
Both are crucial though. Like the time current curve is something that you're going to use for selective coordination, or if you have a device that can only withstand a certain amount of incident energy, you know what I mean? And then the second, the peak let through current is how much it'll actually see and verify through testing. So we hook the fuses up to our generators, and we'll actually pump as much current through them as 10 times rated. So if it's a 100 amp fuse, it'd be 1,000 amps will pump through it and make sure that it'll actually open in that amount of time, and that the energy that will go through will actually be what we've calculated to be based on the design of the fuse.
Got it. So here's one. We always count on Chuck for some different questions, and his question is, what makes Mersen different from bus or little fuse?
I don't know how to answer that without being mean to the competition. So think of it like this. Mersen is one, we put a lot of steps in because we actually do care about our customers at the end of the day. So think of like the cube fuse, for example. We don't offer the cube fuse. It's a proprietary thing that Bussmann offers. The whole fuse coordination panel, which has fuses in it, was designed to be put into buildings for safety features. After the planes crashed into the towers, the lights inside of the stairwells went out, and so they came up with this fuse coordination panel that will actually protect it, branch circuits, and raise their interrupting current up to 200,000 amps. Bussmann came out with a cube fuse because they wanted to corner the market, which it's a very good design in what it is. When COVID happened, which none of us actually saw coming, 3M stopped making the resin that they used for those. Now, you couldn't take a little fuse product or a Mersen product and slap it into those panels. You had to have this proprietary fuse that would actually clip in there. And they couldn't produce it because they weren't even getting the resin. And they went to like 52 weeks lead time, and these things are used for schools and hospitals and things like that. And at the end of the day, we would rather, you throw a competitor's product into our product so that it can turn on and you can use it versus having something that's proprietary. So at the end of the day, it would be Mersen actually cares about what their end users go through. We run into the same issues as everybody else with supply chains. And one of the biggest problems that we had with our competitors is they weren't necessarily being honest with their lead time issues. We would say, hey, it's going to be 12 weeks. They would tell them 8. Our end users would go with the competitor, and they would find out at 8 weeks that their order got pushed another 8 weeks. So it's like they're like, well, now I'm stuck halfway through. They did it just to get a purchase, and it just wasn't. It was kind of a shysty thing to do. And for us, we were always honest, and we're like, this is what we're doing, and we would hope our customers remember that at the end of the day is like, hey, these guys actually told us the truth. They were honest with us. They didn't try and come out with some proprietary information, like proprietary product to corner the market. We care about our customers. We want them to actually have information and the products that they need. And so my job actually exists to make sure that end users actually get what they're looking for. So I'm not a salesman at all. I don't sell anything. I don't have a sales quota. I make sure that reps don't push a bunch of product on an end user that they don't need, that we actually give them the information or give them the products that they need based on what their application is. So we're not just selling them a bunch of switches to make a purchase. We're selling them things that they can actually use for their application. And that's the whole reason my job exists. And I have counterparts all over the country that do this. So short story long, the big difference is, Mersen cares. We actually want our customers to do well and have good products.
So let me thank Chuck for the question. That's a good story.
Yeah, and that one, the cube fuse problem in itself was just kind of an example of the things that happen. And I'm not saying Bussmann's a bad company. I've never worked for them. I only hear horror stories, so I can't base everything that I know about them off of the stories I hear from their customers, because by the time their customers have called me, they're fed up with the competition. So of course their story is going to be awful. Mm-hmm. But from my point of view, it's always just been, when I started with this company, I was here for a year. We had a newcomers thing. I actually met the CEO of the company. The CEO is the big dog. I actually got a dog my first year into getting a company here, and the CEO sent me dog treats and a dog bed. Like, the guy runs a global company. We're in Germany, China, France, everywhere. And the guy sent me a dog bed. So I'm like, that's just the kind of thing that they do, not only for our employees, but for our customers. And it's just like, even with the fuses, we test them up to 300,000 amps. We don't have to. UL only requires 200,000, but we want to make sure that our customers are safe. If an application exists where there's an interrupting rating that can possibly be around 300,000 amps, we want to make sure that our fuse meets that, even though we're not required by code to do it. So it's just this company's a very good outfit.
And one last question, the question from Anthony: did Mersen purchase the EJO fuse line from General Electric?
Yes, we did. We purchased it, I want to say 2010 or 8. It was before my tenure. When we did that, though, we changed out. They used to have a glass body. We changed that out to a ceramic body. We changed a couple of heating elements in it as well, so it doesn't overheat. But yes, we did purchase that from GE.
Brad, thank you for an excellent presentation, and we look forward to working with you in the future.
Yep, and my contact information is in the PDF. If you guys have any questions, let me know. Thank you, guys.
So long. Have a good day, everyone.